Today we are going to look at something again concerning the electromagnetic radiations. We have discussed something concerning UV visible radiation. So today we are going to look at infrared spectroscopy. We are going to look at the principle. We are going to look at the principle. The principle of the infrared spectroscopy. It's commonly called the IR spectroscopy. Now, do not forget to share. I will always say this, share these classes. Remember to share these classes as soon as they get to you. And don't forget to advise that they should also do what? Subscribe to this channel. Dr. B Chemistry class or Dr. B Science classes. And then also in the Facebook page, the same Dr. B Chemistry or Science classes. Do not forget to also share and ask them to follow. Then you can like and comment as the case may be. Thank you very much. Let's look at infrared spectroscopy. Now I want to simply say that, do you know that infrared as it is, infrared radiations are very, very important. As a matter of fact, they are the most important radiations along the electromagnetic spectrum. The infrared radiations are the most important radiations, if I must say that, I must say so, in the electromagnetic spectrum. Do you know that wherever there is absence of visible lights or visible radiations, usually it is the infrared radiations that provide what you can describe as night vision. So they provide a night vision for you to be able to see through the night. And also sometimes in your camera lights or your camera lights where you want to use them at night when there is no visible radiations, it is the IR radiations that provide the possibility for you to do your capturing with your cameras. Do you also know that your remote controls that you use to power your television, to on your television or to control the system and all those things, is built with an infrared radiation. So you can see how important infrared radiations are. There are so many applications. We're going to see that in our subsequent class when we discuss instrumentation. Now, let us quickly put down something that will guide us to describing what infrared radiations and spectroscopy is all about. Okay, now let us look at something of this nature. Now let us look at something of this nature. Now this is a typical electromagnetic radiation. Let's say we have from here to here, and then we have here, we also have a possibility around this region. We have another one here, and then we have this, and it continues. Now if you look at this can be your gamma radiation, okay, and then this is your X-ray radiation. This of course is your UV radiation. This of course is your visible radiation, and here is your IR radiation. That's infrared radiation. And then you also have microwave radiation, and then finally you have radio waves. You have radio wave radiation. Okay, so this is a typical description of the electromagnetic radiation. Okay, so you have the X-ray radiation, you have the gamma radiation, the X-ray radiation, the UV radiation, visible IR, microwave, and radio radiations. And this is the IR, infrared radiations, that we are interested in discussing the principle. Now it is important or relevant for us to know that even at these IR radiations, we still have a division here. We still have a division here in the IR radiations. Okay, so the IR radiation, we have the near IR radiations. We also have the mid IR radiation. We also have the far IR radiations. So you need to take note of that. So this we have the near, okay, near IR, and this we have the mid eye arrow, and this we have the far eye arrow. So we have the eye arrow radiations divided into three: the near eye arrow radiations, the mid eye arrow radiations, and the far eye arrow radiations. Now these radiations that you see here have their own wavelengths and frequencies. Remember that we have discussed earlier, we said the UV visible radiations have a wavelength at the region of about 200 to 400 nm, and the infrared radiations also have that. So at this point you have about 700 nm, and then here you have 1300 nm, and then here you have 3000 nm, and then here in here you should have about 1 million nm. So you can see the wavelengths of these different IR radiations. Now from this point in this way, going this way, you have an increasing wavelength, okay, measured in nm. And then from this side, in this way, if you are going this side, you also have an increasing frequency. You have an increasing frequency or energy. Yes, you have an increasing frequency or energy. And it's important for me to let us know here that this frequency or energy is very, very important, because the entire electromagnetic spectrum is dependent upon what? Upon the energy of the photon. Remember that what controls this electromagnetic spectrum or radiations is the photon. And photon is a very little or tiny particle of light, and it always operates in a wave-like motion. So that is why we talk about electromagnetic waves. So the photon, which is the tiniest or the simplest or the smallest light particle that takes the light characteristics, is always what? Always in a wave-like motion, and that is why you see this moving in this way. And this particular photon has particular energy, and its energy is likened to every type of molecule, whether it is an organic molecule or inorganic ion. So the nature to which the absorption of the molecular structure of whatever you are trying to analyze using IRO depends seriously on the energy that the photon carries. So the photon energy is very important in the analysis of any of these electromagnetic radiations. But like I said earlier, it's important for us to note that the IR radiations are of greater importance, and usually it is the mid IR radiations that are mostly used. Out of the near eye arrow, the mid eye arrow, the far eye arrow, the mid eye arrow radiations are the frequently used radiations in analysis of organic molecules and inorganic ions. Do not forget that. Now, we should know that when you are moving from the far X-ray radiation, the far gamma radiations to the radio radiations, there is an increased wavelength. And when you are moving from the radio radiations moving to the gamma radiations, there is an increasing frequency or energy. So there is higher photon energy in the gamma radiations compared to radio radiation. So that means that the IR radiations have higher wavelength, but have a shorter frequency or photon energy as compared to visible, UV, X-ray, and gamma radiations. Now, if we have an understanding of this electromagnetic spectrum, they narrowing us to the IR radiations or FR radiations, what is then the principle of operation? What is the principle of the infrared spectroscopy? Now let me let us know that the infrared spectroscopy analysis is based on the measurement of three basic items, and one of it is absorption. And then the next one is the next one is emission, and the next one is reflection. Yes. So the IRO analysis is based on the measurement of either absorption, emission, or reflection of radiations. When you pass infrared radiation at the right ranges through a sample, whether it's an organic molecule or an inorganic ion, once you pass an infrared radiation through a sample, something happened. And what happened is that there is going to be a total alteration in the vibrational or rotational energy of that molecule. So it's important for you to also know that what causes the absorption, or the consequence of the absorption of infrared radiation is the effect on the the vibrational or the rotational energies of the molecule. Once the vibrational energy is affected, that is the end. It means that there must be a change in the structure of the molecule. Now, what happened, like I said, is that once the IRO spectrum, IRO radiations are pushed through a substance, a sample, they go directly into the molecule, the molecular structure. Now, there at the molecular structure, what happened is simple. They are going to absorb the radiations with that particular wavelength that is required by IRO and by that molecule. Remember that the IRO is ranging between 700 to 1 million nanometer, the nanometer. So it means that between 1300 to 3000 is that particular radiation that the sample is going to absorb. Since we say the MIRO is the major radiation that the major radiation, of course, that is being used in analysis of IRO. So it means that once you channel the infrared radiations into a sample, the sample is going to absorb radiations at the range of 1300 to 3000 nanometer. And once they absorb the radiation, they are going to cause a change. They'll cause a very fast change in the dipole moment of the molecule. Because the dipole moment is simply the changes or differences in the positive and negative charges of the molecule. So that radiation that is absorbed at this particular range is going to do what? Affect the dipole moment. And once that is done, there is going to be what? There's going to be an effect on the vibrational or the rotational energy of the molecule. And once that happens, there's going to be an excitation of the vibrational energy, okay, at the ground state to the what? Excited state. And once that is done, based on the frequency of that radiation, there is going to be what? Photon excitation. Now, when these photons are excited, they are going to leave you with some sort of information which will be read as a spectrum. And once it is read as a spectrum, you can be able to gather so much information from there. Like we're going to see that in our next class when we talk about the instrumentation of IR. So once you have, like I said, once the sample absorb radiation, the first thing that will happen is that there's going to be a change in the dipole moment of the molecule. And then the internal structures, vibrational energy, and rotational energies will also have an effect such that there's going to be an excitation from the ground state of the vibrational energy to the excited state, hence leaving the photons that opportunity to do what? To excite as well. And once there is that excitation by the photon, consequence upon their frequency, because the energy that the photon carries allows for what? Allows for multiple excitations. And once there are multiple excitations, there are also multiple peaks that you get, absorption peaks that you get. We are going to look at absorption peaks in our next class. So once the photon energy is such that it can be consistently excited, you are going to have also consistent peaks, absorption peaks that you will get. And once these peaks are obtained, the peaks will be read at the display unit, where information that is required from IRO, special information like functional group determination, will be obtained at the end of the day. Now that is the simple principle of the infrared spectroscopy. Do not forget that everything boils down to the fact that there is going to be an absorption, this time not UV visible radiations, but absorption of what? Of infrared radiations at the range of 1300 nm to 3000 nm, and that is going to hit on what? On the dipole moment of that particular molecule, in that substance you are trying, or sample you are trying to do what? Carrier analysis. And once that happens, it will affect the vibrational energy and also the rotational energy of the molecule, hence causing an excitation of vibrational energy from the ground state to the excited state. And once it does that, due to the photon energy and the possibility of a constant excitation of that photon at that particular level, there is going to be a production of absorption peaks for IR, and those absorption peaks will be read in a display unit where you have absorption of transmittance against the wavelength, and they will give you peaks that will gather information, of which one of the major information is to do what? Analyze the functional groups of the molecule. Now that is the much we can take today for this class and the principle of IR spectroscopy. Join me in the next class where we will look at the instrumentation and application of the infrared spectroscopy. Until next time, please do not forget to share this class. Don't forget to subscribe. Don't forget to also go to the Facebook channel or Facebook page, and do same by following this class and share this class so others will be part of it. Until next time,